Hello, hello. These are flipped notes 3-5 in the sensation and perception unit. We've talked about vision and we've talked about hearing, so now we've made it to the other senses. My Bitmoji is saying, because she just ate something yummy, and it was one of her senses that helped her to taste that. Let's get into it. So, smell and taste are known as the chemical senses because it is chemicals in the air or in foods and things that we eat or drink that are stimulating our sensory receptors. We don't just say smell and taste, though. Our sense of taste is known as the gustatory system, or maybe you want to say the gustatory system. But gustatory system is taste, and then olfactory is our system of smell. It smells like an old, stinky factory. In both of those, there still has to be transduction that's occurring, that these chemicals that are coming from food and particles that are in the air have to still be converted into neural impulses that can travel through the olfactory or the gustatory nerves to different parts of the brain. One of the unique things here, remember, is that smell does not go through the thalamus, that it's going to have a direct link from that olfactory bulb to the olfactory cortex. We're not going to get super into in-depth here with smell, but looking here at this zoomed-in version of what's going on up at the very top of our nasal passageway. This is how we're going to detect an odor or a smell. All this is part of our olfactory system. So that odor is going to go up and it's going to hit cilia or tiny little hairs. And it's going to stimulate these different receptors. And these are those similar to what's in your eyes. It's kind of like a bipolar receptor here. But it's going to travel all the way up to the olfactory nerve and into our brain here. It's almost kind of right on the edge of the frontal lobe and the temporal lobe. For detecting a taste, the taste buds include the taste receptors, and that's where transduction occurs for our gustatory sense. So on the surface of the tongue, it's actually really bumpy. Those bumps are not actually taste buds. Those bumps are called papillae. There's a few different types, fungiform, circumvallate. Anyways, you don't need to know all the types. Just know the bumps are called papillae. And in between those bumps, there are grooves. And in those grooves, so here's a groove right here in between those bumps, lining those grooves, that's where our taste buds are. That's these little purple things here. And at the bottom of a taste bud, there are taste and basal cells, and that's what's doing the transduction. So those chemicals that we're detecting in our food or drink, they're in our saliva. The saliva gets into these grooves and it stimulates our taste buds, and that triggers transduction to occur along the gustatory afferent nerve. We've kind of got a picture of the brain, and it's actually kind of being peeled back here a little bit because the gustatory and olfactory cortex are there kind of underneath the frontal and temporal lobes. So our taste sensory pathway starts with the tongue, where chemical particles are stimulating our taste buds, and that's where transduction occurs. The neural impulse travels along the cranial nerve. There's actually 3 different cranial nerves, to the thalamus, to the primary gustatory cortex, which is by the frontal and parietal lobes. For smell, smell is located in the front of the brain, just above the nostrils. The olfactory cortex is also in that same general area in the frontal and temporal lobe. And one of the things we do want to remember about smell is that smell is very closely related to the limbic system. And you'll recall from our last unit that the limbic system is all about emotions and memories. So smells really do trigger memories from the past and different kinds of emotions. Whether it be a stinky smell and it just kind of makes you mad, or a very calming smell, like what might be used in aromatherapy. Also very closely tied to where memories are formed. So a smell can maybe remind you of a grandparent or a candle that maybe somebody you know used to burn. So close ties with smell and the limbic system. Our smell sensory pathway starts with the nose, and then chemicals hitting the olfactory cilia where transduction occurs. Then that neural impulse travels up the olfactory bulb and the basal frontal temporal lobe. Now, for smell to occur and for taste to occur, that means those chemicals actually had to make it into your nose. So think about that. When there's something stinky, like you walked into the bathroom and it smelled like poo, in order for you to smell that, some of those particles actually had to get in your nose and touch and stimulate your sensory receptors. Think about that. You can keep wearing that mask now, right? All right, our next one, I'm actually going to skip this slide. What about flavor? Where does that come from? Flavor is a result of sensory interaction between both taste and flavors and smells. So there are only 5 different tastes that our tongue can actually detect. There is bitter, sour, salty, sweet, and a newly identified one, not that new anymore, but newer than the others, and it's called umami. And it has kind of a Japanese sounding name because it was the Japanese who discovered it. And umami is sort of a savory flavor. So all of the different tastes that we detect are a combination of these other taste qualities. But flavor also depends on temperature. Think about the difference between cold sliced cheese versus hot melted cheese. Odor affects flavor if it smells good or if it smells bad. The texture of it, and then just the overall taste of the bitter, sour, salty, sweet, and umami. It used to be thought that our taste buds on our tongue were kind of divided into different regions, that you could only detect sour flavors on the side and salty and sweet flavors on the tip of your tongue, and that the middle of your tongue didn't really have any taste buds. But that has since been discredited, and researchers now say that you have all the taste buds all over your mouth, including all around the roof of your mouth, the side of your mouth, and even at the top of your throat. You can detect flavors way back there as well. And again, those 5 basic tastes: salt, sweet, umami, and some other examples there. We have soy sauce and Parmesan cheese as examples for umami. Bitter, as in cocoa or coffee beans, and then sour, like lemons, limes, grapefruit. What about some of the weird things people like to eat, like grub or bugs, or fish eyes? That's what this little kid is trying to do, is poke out some fish eyes. Or this one where they're drinking fresh blood from a cow. Like, why do some people think that tastes good and others don't? And it's really just a learned preference, and it's cultural, that if you were exposed to those things early on, you'll eat them and maybe you'll like them. So really nothing unique about their specific taste buds. It's just a learned preference. The next sensation we'll talk about is the sense of touch, which happens through the skin. The skin is the largest sensory organ. It's all over the body. That's one of those common Jeopardy questions about what's the largest organ in the body. And people think, oh, it's the intestines or the stomach, but it's actually our skin, because our skin is considered an organ. The skin can pick up on touch sensations, pressure, warmth, cold, pain, even fine touches. So a touch would be like putting your whole hand on your arm, but a fine touch could be like poking with a pencil tip. So there's a difference in the different touch sensations. And they're usually a combo. So for example, the sensation of damp is a touch sensation plus cold usually. We have about 1.5 million receptors all over our body for touch and pressure, and those are processed by the somatosensory cortex in the parietal lobe. Touch, probably the key part of touch is not just feeling good touches, but pain. There's different ways we experience pain. There's a fast pathway and a slow pathway. The fast pathway is that immediate reflex that we get from our spinal cord. That when you experience pain, you get a reflex that goes from the spinal cord and then back to the muscles. But you also have a slow pathway that's going to continue to send the signal all the way up to the brain, up those afferent or ascending sensory neurons, and then send a signal response back down through the efferent or motor neurons, going back to the sensory receptors. The gate control theory of pain says that we actually might have the ability to control how much pain we're experiencing to a point. So it describes that at the top of the spinal cord, there's a hypothetical gate, and only so many sensations are able to pass through the gate at one time. So when you bump your elbow, you have pain sensations going through the gate. But if you rub your elbow, now you have both pain and positive sensations. You can't have too many. There's only a certain amount will fit, so not all those pain receptors will go through there. So the idea is that if you can create sort of a contrasting signal that blocks the pain or divert your attention, then you may not feel as much pain. This only works to an extent, you know. If you sever a toe, it's not going to help just to rub your toe. But that's the gait control theory. An alternative source for pain release could be done through acupuncture. Acupuncture, where they insert needles into specific pressure points throughout the body. Some theorize that the reason it works is that it causes a release of endorphins, and that we know endorphins are used to block pain as well. Others say maybe it's just a placebo effect. Here we have this gait control theory showing incoming pain pathways, but you can also control it by adding additional sensory feelings like rubbing your elbow or distracting your attention. And those signals are going up to the somatosensory cortex in the parietal lobe. A couple more senses that we just barely reach on here. The kinesthetic sense is our sense to know the position of our bodies and the position of our different limbs. So this goes with movement, posture, muscle functioning. This is what allows you to do multiple things at once, like walking without looking at your feet. People who have a strong kinesthetic sense might be good at dancing, playing the piano, where they're able to move their hands different ways and their feet as well at the same time. A baseball player, like a pitcher, who's able to control the movement of his arm and his wrist. Even a surgeon who's able to control the movement of their wrists to a very fine amount. But they're able to control the position and motion of their different parts of their body. Our vestibular sense is our sense of equilibrium or balance. And we talked about this a little bit in the last section, because the vestibular sense is processed through the semicircular canals, which are located in the middle ear. And there's fluid in there that is constantly moving around. And our brain is able to detect where that fluid is, and if our head is right side up, or if it's tilted, or if we're upside down, based on the movement of that fluid. When our brain gets confused, say we're in the car and we're traveling 70 miles an hour. So that fluid is still moving a little bit, but you're still, maybe you're trying to read at the same time. Your brain gets confused because the vestibular sense says, hey, we think we're moving, but it also seems like we're sitting still. Or if you are spinning in a circle and then you stop, but that fluid continued to swoosh around, that's why you get dizzy. Your vestibular sense says our fluid is still moving, but we've stopped. What's happening here? And then you get dizzy or confused. And again, there's those semicircular canals located in the inner ear that are filled with fluid. They stimulate a vestibular nerve that the brain can process. That's it for the sensation half of our sensation and perception unit. And that's it for Flipped Notes 3-5.